welcome back to Sigma Lectures after a week's hiatus. I was at the grad thing last week on Monday, so we didn't run one. We didn't run the Sigma Lectures. But this week we're talking about Shear. So I hear that the assignment's coming out tomorrow as of the recording of this video. Yeah, so
what's your comment on this?
I have no comment. I can't comment on the assignment because it's not out yet. But I bet my top dollar it's on Flexure. And it might...
Or your left nut.
Yeah.
Alright. Both!
No comment on that. No, but yeah, I bet it'll be on Flexure. It might have Shear in it. I believe last year it didn't. But if he wants to make it harder, it's a natural progression because basically actually I think I have a comment written here. See that red text there? Basically Shear design in the steel standards is under the same chapter as Flexure. So it's like an extension of Flexure. Okay. I'll tell you why. Maybe I'll start with that because I've ordered this kind of weirdly. Should I give you a look ahead first of what's to come? Okay, maybe I'll do a quick because this overview thing that I've got on this first page. There's a lot more that I've packed into this than previous weeks. Just because there's more steps, but each step isn't as difficult to understand. So buckling is probably the hardest thing to understand in this course. Shear, I feel like you guys will understand quicker. So it's just more stuff, but don't be scared. Like it's I feel like each step's easier, right? Okay. So we're gonna talk about what flexural shear is. That's what I'm trying to get at. There's two types of shear. There's flexural shear and there's punching shear. Now, punching shear is something that more relates to slabs. So, for example, reinforced concrete slabs. You don't really touch that in either core course for steels or concrete. But if you go on to do advanced concrete, if you go on to be a structural engineer, punching shear is a pretty important concept. We just talk about flexural shear here, right? I'll get back to that. Shear design has a couple of checks. There's basically four. I've broken it down into four. One is minimum web thickness. Okay, these I might just list them first, and then I'll explain them later. The second one is web shear capacity, and that'll be like the majority of shear design in quotation marks. Okay. And then the third one is shear and bending capacity. So here's where shear relates to bending. It's basically if your beam is experiencing shear loads and like it's in bending, it kind of reduces its capacity. It's kind of being like attacked from two angles, I guess you can think of it like that, right? So there's this combined action that we have to check for as well, right? And the fourth part, which I'm not even sure is going to be in your course, like there's lecture slides on it, but I'm not sure if it's accessible or not. You might need to ask Brian. It's called load-bearing stiffeners. It's all still to do with shear, but it's kind of like an additional check, an additional bit, which is quite sizable. So I'll still run over it, but I won't put as much importance on it in this yap as the other stuff, okay? Wait, does anyone have questions right off the bat or not? Okay. So before I even get onto this, I'm going to show you this picture at the bottom here. Don't worry about the stuff I just skipped, I'll come back to it. So here you can see like a beam, so that's the horizontal member, and we're applying a load to it. So here we're just showing it as cylinders, right? But this is it's a generic example. Essentially we have this going on. So these are our supports, and that cylinder acts as like a point load on it, right? And we have our beam that does like this. So it's kind of more similar to what you'd see in engine mechanics or something, right? So basically what it's saying is if the supports are really close together, and that there's that load being applied to it, and you have this really short span, right? It almost acts in compression. Do you guys kind of see that? So like this part of it is being compressed, right? Okay. So moving down one, the supports are moved further apart. We've got a greater length, and you just have to imagine the point load being applied at the same spot in the middle, right? But we've basically increased our span of our beam, and we still have that point load being applied. And what happens here, I'm going to erase what I drew a little bit because it shows it there, is this is kind of the danger zone for shear. So shear is that diagonal shear failure. Sometimes it's called diagonal tensile failure. So basically what I'm trying to tell you in saying all this is shear is kind of a difficult thing to grasp. Like the steps that you do, like in this topic, if you just follow it mathematically, everything will make a lot of sense. But trying to visualize shear is kind of hard. That's what I'm trying to say. Okay. And this is also another type of shear failure. So we've done a similar thing. The span has just increased. Our supports have just gone further apart. It's still shear, but it's kind of a like a horizontal shear almost, right? It's like called a interlaminar shear, whatever, right? It's still considered shear. So everything we design around in this part is going to be related to that. But when your span gets long enough, so imagine like a simply supported beam, and it's quite long, and you have a point load just in the middle, it's most likely going to fail in bending. Because bending, as we know, is heavily influenced by length, like the length of the beam. So do you guys remember this formula from edge mechanics? So say we're trying to find the M star in the middle, or M max, or some shit like that. Do you guys remember the formula for that?
WL squared on H.
Very good. So L has like a quadratic effect on your moment. So the longer something is, like the more moment it cops basically, right? Yeah, so like a simple kind of way to understand whether shear will govern your beam or flexure will govern your beam is basically if your beam has like a fairly short span and it has point loads, right? That's kind of where shear is dangerous, because if you think about the bending moment diagram for this, right? So this is your free body diagram. If you think of think of the shear force diagram. Your shear force diagram will look something like this, right?
Huh? Why?
Reaction goes. Oh, sorry, not for that. I was thinking. Yeah. Actually, I'll do it like this. Yeah. Right. So, basically, this point load acts as a big discontinuity, big jump in shear, and that's dangerous, basically, for for shear of a beam. But if you have like a uniformly distributed load on the whole thing, it'll be more like that. And what will probably be more critical is your bending, assuming you have a long span or something like that. Anyway, I'm kind of yapping, but do you guys kind of get the why flexure and shear are closely tied together? Yeah.
Are each of those failures like only associated to how long they are? Like, can a different, like one of those failures happen at a shorter?
Oh yeah. So shear. Okay, think of it like this, right? Bending will only really govern when your span gets long enough. We know that because do you remember the little red book table I showed you?
Yeah.
Do you know how lateral torsional buckling is more susceptible when like the length is longer and shit like that?
Yeah.
Actually, I'm kind of that's a bad. I'm talking about something that's kind of not related.
Like the general rule that the longer something is, the more like it's.
Yeah, it's gonna be worse at bending. So like a bridge, right? A lot of the bridges you see, they're going to be suspension cable bridges, which are tension based for capacity, or trusses, because trusses are way better than beams with a long span. Because if you just have a bridge that's only a beam, a bridge is supposed to be really long, right? It's gonna get fucking demolished in bending, basically. Yeah. Yeah.
Do we ever see vertical shear failure?
So for something to take on vertical shear, so say you have a column, you need to have a point load or something going that way.
Yeah.
So like,
No.
it's pretty rare. Dynamic, like a plane hits a building or something, right?
Okay.
I don't know. No, basically.
No.
Yeah. Oh, earthquakes. Yeah, sometimes. Yeah.
Wait, to shear the example downwards.
Yeah. So
Like a
shear.
beam. Like these ones.
Yeah.
Do we ever see a vertical shear failure?
Yes. Oh.
That's what I said. Because like you've only got diagonal and
Like the beam
like
snaps like boom.
yeah, like a snap.
Not really, because I think it's to do with the Moore circle and like materials like weakest plane. It's usually some diagonal angle. Yeah, I want to say that's the reason. It's usually not that. I don't fully know, to be honest. I don't know the solid mechanics behind it. Even punching shear will kind of fail like on a diagonal angle. Yeah.
Oh,
Okay.
really? Well, what if you want to punch something?
That's
like in manufacturing. You'd want it to be straight.
Oh, then it's more a mechanical engineering issue, not a structural engineering issue, because that's like a engineering dynamics thing. Yeah. Okay. So that enough of that.
Enough yapping.
Okay, we're on the same page, kind of. So I'm talking about things which aren't really in the course. So let's go back. Let's get back to it. So I-beam, right? Looks like that. Okay. Sorry, it's a little bit pixelated. An unstiffened web. So firstly, what's a web? You guys remember the terms?
The web is the middle part of the flange. So
Yeah, that's right. So you have an I-beam. That's a flange. That's a flange. The web is this. And it's to do with the part that has a smaller width. That's what a web is, right? So in a concrete T-beam, that's the flange. The bottom part there's a web, right? Same thing. Got it? So, when we say we have an unstiffened web, what do you think that means? What do you think that means?
The web is not stiff.
Very good. So, firstly, beams, right? You can select a few different steel products for beams, but generally use I-beams because they're so good in bending, right? Like you can also use hollow sections. There's a few options, but like let's just talk about I-beams basically, right? I-beams have the one web and two flanges, and they're susceptible to basically. Sorry, I'm not doing this very well. So basically, imagine there's point loads here, right? Imagine that there's a point load in the middle, right? What might you expect to happen to the web of the I-beam if there's like a high point load in the middle there? Because basically, you like just a universal beam is good in bending, right? It's really good in bending. And when we're talking about bending, we're generally thinking about like, what about like uniformly distributed loads acting on it, and then it can kind of resist it because it has that bending moment that's like that, right? But if there's a point load, suddenly this part here can get crumpled, basically, right? Yeah. So say there's like a really fat person on there or something, right? That middle part is taking a lot of concentrated action, and that's essentially shear, right? And you basically need stiffeners, right, at some point to resist it. But without stiffeners, this web is called an unstiffened. Yeah, this is called an unstiffened web, basically, right? So a stiffened web looks like this, essentially, right? We have these kind of rectangular plates, which are usually welded onto the I-beam to give it additional resistance, basically, against certain points that we're going to expect to receive high concentrated loads, right? So reactions. The reactions, like whatever this is sitting on, what might be a good example, right? So, my ruler. Okay, pretend I have my ruler, and I put it between this table and this chair, right? And I just push down on the ruler like that, right? Where are the loads gonna be highest? Yeah, pretty much, right? We have the middle, the force, the point load in the middle, and then two reactions on both sides. So those are also point loads. Reactions are point loads, right? And so if you're going to put in stiffeners at the point load, you should consider putting them where there's the reactions as well. In this case, we've got one point load and two reactions. So and it's even, right? So how much of the point load is each reaction taking? Half, right? Okay, say we had 2 point loads and this is still even, right? How much is each reaction taking?
Half of the total.
So now this is matching, right?
Wow.
Okay, what if there's 3 evenly distributed point loads? Which one's taking more now? The reactions or the point loads?
Reaction.
The reaction is taking more. Because it's 3p divided by 2 on each. So it's 1.5. Right? So yeah, anyway. Now we've got something that looks similar but slightly different. These are called your intermediate... Sorry, the name for the ones that the reactions are called load-bearing stiffeners. Right? Which, if we rewind, because I had to go through some terms before I could explain this. That's what this fourth check was. That's the thing that's going to be optional. Asterisk. It's going to be something that we talk about at the end, but maybe not as much in detail. It's the design of these, basically. So load-bearing stiffeners are the ones which stiffen the support. And the point load, sorry. So load-bearing stiffeners are what I've highlighted in blue here. The ones in purple are intermediate transverse stiffeners. So what do you reckon these ones help with? Like tension, compression or something in the beam, or?
Yeah.
Shear.
So in terms of like shear forces, the highest ones are going to be at the load-bearing stiffeners, basically, right? It's going to help the beam not completely crumple there. The intermediate ones are more because the spacing of these matter. So if you more regularly space them, they're going to assist in resisting that crumpling action. It's kind of like
So it's resisting shear.
yeah, I mean it is resisting shear, but it's like if you space them more closely, they're gonna help at both the reaction and the point load, right? Yeah, rather than because you can only put one thing directly at those points, so you might as well put one in between as well. That's
dependent on how long the span is.
It's called the spacing. So yeah, S is basically the distance between stiffeners. If you reduce that spacing, so say I put 2 stiffeners like here and here instead, that's gonna help even more, basically.
Why not make the stiffness thicker?
Yeah, that's another thing you do. But at a certain point, It is like diminishing returns.
I mean, instead of space, you can.
It's a similar concept, I think, to restraints. You can only restrain it so much, but how regularly you space the restraints. I'm talking about like restraints for flexure or something like that.
Oh.
You'd rather have regularly spaced restraints than like a mega restraint at one point, but then there's like a bunch of unrestrained beam. Similar idea with stiffeners, I think. You want more of the beam's web, the total beam's web, to be stiffened. Yeah. Okay. Any questions so far? So I'm just running through some definitions essentially. Stiffened web, unstiffened web, yeah? Okay. So shear stress, right, is this one represented by tau. There is a formula for it, but I won't go too in depth with this at the moment. This is just for your information. And we've got tau max and tau average. That's my notation for it, but in the code, they call it FVM and FVA. That means max shear stress and average shear stress. So here I've drawn it. This probably helps with the understanding a bit better. So just pay attention to the drawings real quick. The easiest one to understand is the one in the middle here, rectangular. Okay, so basically, you've probably seen this in solid mechanics. It's your shear stress distribution. The way that they mapped this curve was using this formula, basically, right? So it's whatever the external shear force was at that point. First moment of area, which is mapped with depth, right, which is y. And then these are constant for the shape of the section, right? So, for example, if this was a rectangular prismatic beam, we've just cut in the middle here, right? We know that this shape has a constant I value, has a constant width, right? And what was the other thing? Area, right? So let's call that section AA. That's this rectangular shape section, right? We follow. So you can find whatever value we have for shear here, plug it into the formula, map it against the depth y. I guess you can go this way, or you can go this way, right? And that's how you get this curve, right? Are we following?
So the shear is constant, the I is constant, the width is constant.
Yeah.
But the moment of area changes.
Oh, so yes, yeah, first moment of area. So here's the formula. This y changes with depth, and it ends up being a parabola shape.
So the area is from which area do we take?
It's a good question. I believe it's the area above the neutral axis or something like that. Oh no, I think you. Sorry, I think what I did when I did there's a calc for it. I think might have included it. Let's say this is positive y. That's negative y, and then the middle is I think what I did was
The further out you go, the bigger
yeah.
the moment of area.
So that's your area. What I've done in A, and then in the middle here, that's y hat for whatever shape, I think. Yeah. So then area is like b times height. Yeah. Anyway.
Yeah.
There's like algebra behind it, but it becomes a
But then wouldn't the shear
y
stress
squared.
be biggest at the edges? So the area and the distance is bigger at the edges.
I might have set the coordinate system wrong. It might be this way. Yeah. Do I have it?
I don't know.
Okay.
You
I can't remember how the algebra works. Sorry.
need to know how the algebra works?
If you have a custom section and it asks for shear,
You're probably, yeah.
yes, I'll say yes if you have a weird shape. You do need to know how the algebra works. This is the one part of the course with this whole like calculus thing going on. Yeah. Okay. Sorry. Let's go on. So basically, for us, basically the tau max is going to be in the middle, right? So the middle is going to cop the most shear stress, essentially, right? That's going to be important later when we talk about capacities and stuff. But for an I-beam, basically, right, what tends to happen is that your max shear stress, basically, okay, if I was to overlap them, here's the shape it would be for a rectangle. Here, and then the shape you see there is essentially it's considered more flat. So this part's like more flat. So what it's saying is it's considered uniform shear stress, quote unquote. Whereas the other ones are considered non-uniform. Because the max compared to the average value that it is, right? So if I just was to draw the average value for this one, it would be like here or something. And then that's the max, right? So that number is less than 1.1, that ratio. Whereas the average for this one, which I've drawn all over, is probably like here. Maybe that's not. Here and here for the max. And that's greater than 1.1. So that's what is that definition. Like uniform shear stress distribution versus non-uniform for the shape, right? And yeah, definitely for the unequal flanges. So this was the section which was in the assignment last year. Yeah, it's pretty rough. So average might have been like here, and then the max was there. So that difference is not 1.1. You know. Okay. You following, Sue? Okay. So that's basically all the preliminary stuff I wanted to talk about, because I'm going to use these words a decent amount. For example, like spacing. I might talk about clear depth, right, between flanges. So that's a flange, that's the flange. Clear depth is the distance excluding the flanges, right? So basically the height of the web, I guess you can call it. Yeah. Okay, let's talk about the requirements. So the first one's the minimum web thickness. So we know what the web is, right? The web is the thin part of the I-beam, basically, right? Like that's the web. So there's different rules based on whether it's stiffened or unstiffened and how many flanges is bound between. So everything's definitions. So that's why you kind of need to know the definitions pretty well, right? Just get used to the terms, right? So web thickness, when we're talking about web thickness, that's TW, okay? There's a minimum, right? It can't be too thin, otherwise it's gonna crumple, right? Regardless of everything else, like in shear design. So say you have a really small amount of shear load and everything, you still need a minimum web thickness essentially, right? That it needs to satisfy. Okay, so if it's bound between two flanges, this is the formula. D1. What the fuck, right, games? Okay. D1 is gonna be D1 is the clear depth, right? So we talked about clear depth. That's the height of the web excluding the flanges, right? Makes sense? Divided by 180, and you take into account the yield of the steel, right? The yield strength, right? Makes sense? Similar thing, but now we have a like a T-beam, right? So before it was an I-beam, now we have a T-beam. So that's attached by one flange, right? Transversely stiffened webs I've drawn it here. Everything's very visual, right? So transverse stiffeners are the ones we've talked about. We haven't talked about longitudinal stiffeners yet. Transverse stiffeners means they have load-bearing stiffeners / intermediate transverse stiffeners. Now keep in mind, you wouldn't have intermediate stiffeners, you wouldn't have this blue one, if you didn't have the red one, right? So you need the load-bearing stiffeners if you need stiffeners, and if you need even more help, you add in the intermediate transverse stiffeners. It's stupid to have intermediate transverse stiffeners without load-bearing stiffeners, right? Okay. There's different formulas. I'm not going to bore you with the formulas because you can fucking read them, right?
Yeah.
But you understand the definitions, right? Because everything is in the definitions. It's like you need to understand the language in order to do the questions and stuff, right? Okay. Here we've got the next case is you have your transverse stiffeners and you have your longitudinal stiffeners, which is the blue one, which runs laterally like that, right? Now it'd be stupid to have the blue one that runs laterally if you didn't have the fucking red ones that run vertically, because that's the whole point of the stiffeners, right? They're stopping the point loads from completely crushing your fucking web, right?
What if you only had longitudinal shear?
So your beam is like, oh, no, it just doesn't happen. It just doesn't happen because like that becomes like,
There's no point in that.
yeah.
Oh, if you turn your beam into a column, then it's the same.
But then it's compression and shit like that.
Oh yeah.
Yeah.
So I can't use shear design for compression.
You'll see that compression and shear, it just depends on your perspective. Because when we design these load-bearing stiffeners later, right, the red ones, and you see this point load on it, it's a fucking column that's buckling.
Yeah.
So it has a compressive buckling resistance,
Yeah.
like as its capacity. So compression and shear, it really just depends what perspective you're talking about. Because for the beam, right, the beam's a horizontal member, it's shear force acting on it. But for this fucking vertical stiffener, it's a compressive load. So, yeah. Anyway.
Anyhow.
Yeah. Okay, anyway. My point is, more formulas. And boom. There's even this part of the code for two longitudinal stiffeners.
Are these on AS4100?
But I made this in Bluebeam at work because I had spare time.
Oh, this is so pretty.
Yeah. So Brian only in his slides, I think. Oh, not Brian. This is like all the steel slides.
Bruh.
I think he just has this version, the stiffened web version,
Yeah.
and he had this one, the unstiffened web. I've done the attached by one flange
Ooh.
and the
double.
stiffened web without the longitudinal stiffener, and I've done the double one as well.
Wow.
So these are they're all visual, right? It's much easier to understand what these fucking words mean when you can see it, right? Oh, and just keep in mind DP. So D1 is your clear depth between flanges, right? DP is your clear depth between your flange to a longitudinal stiffener, right? So from there to there, right? Okay. Any questions about minimum web thickness?
No.
Okay, minimum web thickness should not take you long. It's one line of working. You just have to figure out what case you're talking about. Okay, next is web shear capacity. So we want to find VV. VV is the web shear capacity. And when we're talking about web shear capacity, we're talking about the web of an I-beam or the web of a rectangular hollow section or square hollow section or whatever, right? And it's taking on the majority of the shear force, right? So do you remember how we had the I-beam before? And we saw that its shear stress looked like this, right? The web takes on like 90% plus of the shear because of how it's designed. And we know that. Do you remember how this is what our our stress distribution looks like for axial stresses and bending? And if we think about it in terms of forces, right? this part has a larger width, right? The flanges have a larger width than the web. So the forces that are being taken is like a majority over here and like a tiny bit for the web. So an I-beam is super optimized because the web takes on the shear, the flanges take on the bending. So it's like cooperative action, right? So that's why it's like a million times more optimal than just having steel, like a solid steel section. Because you have these specialized parts of it, the flange and the web, that do different things. So you're getting more bang for your buck, basically. The other thing is that, sorry, I'm kind of tangenting, but the other reason you don't see like a solid steel section, other than the fact it's really fucking heavy, is because yield strength is inversely proportional with thickness. So the thicker you go, the lower your yield strength is. So you actually want really thin members, like how an I-beam has it, because you get the maximum yield strength out of it. I think it's to do with how the steel is hot rolled and then cools down, because it's cooling down at like the outside cools down faster than the inside, and the inside just is like this molten mush for a long time if you have like this really thick rectangular section. Anyway, I've been thinking about that. It's nothing to do with this right now, but yeah. Anyway, my point is, we're designing for the web in shear. We just care about the web because the flanges, they effectively don't take any shear. Got it? Okay. So we generally care about AW, which is the area of the web. We can be conservative and just pretend that the flanges don't do anything, essentially, in a lot of these formulas. Okay, so there's two failure modes we have to consider, right? The first one's yielding, the second one's web buckling, right? So with the whole idea of shear-based compression, you can think of it like, yes, it's shear in terms of the beam, right? Because the beam's sideways and then the shear is acting perpendicular to it. But in terms of the web, the shear is acting parallel to it, and it's causing it to compress like a column, essentially, right? Or like a wall, I guess, right? And so the first one is this like crippling, the web crippling, which is like a just like compressive yielding, right? The other one is compressive buckling, right, of the web. So we have yielding and web buckling failure, okay? Now, here on the side, I've also put down what to expect in the next slide. I've said that the shear yield capacity, it's based on whether you have a circular section or not circular section, right? That's the two types, right? Circular or, say, an I-beam, right? This next one, two for different formulas based on whether the web is stiffened or not, right? So the first case, stiffened. It's got these plates welded onto it. Unstiffened. Okay. The next one. So the next step is we have to calculate what the shear capacity is for a uniform stress distribution. Now we said that a couple shapes, like I-beams, we assume as uniform. And say like a unequal I-beam is non-uniform. For both these shapes, we still need to calculate step 3 first, okay? The idea is if you have a uniform shape, like the I-beam, you calculate this step and you set it as VV straight away. It's like the uniform shape is the uniform stress distribution is the the uniform shear stress capacity is the web's capacity. Done, right? But if it's not uniform, you have to calculate what it would be if it was hypothetically uniform and do an extra step to account for the fact that it's not uniform. Got it?
How would you
It's not assume. You know. So for standard sections, right? Universal beams on one steel, all of them are uniform. All of those UBs are designed to be uniformly distributed shear stress distributions, right? If you have a custom shape, you might not know, so you have to calculate it. So that's where you have to go back to first principles, that thing I showed earlier, and prove it, right?
Yeah, sure.
Yeah. Okay. And this is based on whether the web will buckle or not. Yeah, we'll see that properly later because I don't remember what I wrote for that, to be honest. And then lastly, the shear stress. The shear capacity is based on whether the shear stress is uniformly distributed or not. That's kind of that thing I was talking about earlier. We'll see all this in action, but I just want you to know that definitions are really important, and these things are going to get really confusing. You're going to see VW, VB, VU, VV. Like, there's a linear order to calculate things, and it's hard to wrap your head around if you don't know what the words mean. But it's really easy to do if you do know what the words mean, right? Because none of these things are even close to how hard flexure was to understand. So yeah, what are you gonna say?
Is this like in order of like easiest of like what to calculate, or is like?
No, you have to do it. You have to do it in this
So
order.
you have to check the failure mode 1 first.
Yeah. Failure mode 2. The formula depends on failure mode 1.
Oh. Okay.
It's yeah. I don't know. You'll see VW in this formula, so you need to calculate this order. Yeah. And you'll see both of these in VU's formula. And you'll see VU in VV's formula.
Okay.
So you have to do it in this order, basically, yeah.
Sure.
So, if your section is circular, if it did I fuck it up? Oh, sorry. I'm gonna fix this in the notes. This is non-circular, right? Wait, no, I lied. I did it this way. I've kind of done it slightly differently to how the slides have presented it, the standards have presented it, because I think this is a better way to fucking present it. Dude, it's so pixelated. Oh man. Maybe if I exit and rejoin. Come on. Oh god, it's just as bad.
This is raining.
My internet's is shit. Dude. Okay, it's getting better. So, if your section is circular, you have this formula, and you skip every other step, basically. So you can go straight from step 1 all the way to step 4, if your section is circular. You just plug it into this, and then you can set it straight away. That's just a hard rule. So, but if it's not circular, which is most of the time, like you have an I-beam or something, you have to start doing this.
How do we do? Let me find it. How do we do shear max and shear average for a circular?
Oh, a kind of steps. Oh, for a circular?
Yeah, we don't need to. Because it'll always be uniform.
Yeah, that's true.
Okay, that's awesome.
Yeah, that's true, actually, yeah. You don't need to find out if it's circular. Okay, next, shear buckling capacity. Step 2, right? So, again, I said this is if the section is stiffened or not stiffened. Sorry, if it's unstiffened or it is stiffened. There's 2 different rules, right? So this comes back to definitions. S is the spacing between stiffeners, right? And dP is... I'll just show it visually. It makes more sense. dP is that. Or if there's not a longitudinal stiffener, it's that. And spacing is that, right? Easy. And then you just chuck it into this big fat formula. But if it is stiffened, right? Sorry. So even if it's if it's unstiffened, it actually looks more like this. I should make this clear because this is a stiffened web, right? Just imagine this is me drawing the unstiffened web. If there's no stiffeners in it at all, your spacing is just the same as your span, right? And then your clear depth is equal to dp. Got it? Yeah. Okay.
Oh wait, sorry. What was the case if there was no horizontal stiffener? It was just the.
D1.
So
D1.
yeah,
Okay.
yeah. Just ignore these blue ones, and then dp is d1.
Right. Yeah.
Yeah. Okay. So if it is stiffened though, we have to do a couple more things, right? So it's not just as simple as using this formula. This formula doesn't apply to this alpha v. What you should do to get alpha v and alpha d is use the table below, basically, and then alpha f is something else, which I'll show you below as well. So the table is this, right? You have to find. Oh, fuck! It's annoying that it's pixelated. It's slowly clearing up. So you have to find this formula, calculate it, the blue one, and then find the green formula, which is just the spacing over dp, right? God damn. It's that, right? And then you line it up for the row and the column, and you find the closest number on the table. That's the fastest way to do it, because it calculates two of your constants at once, right? And then alpha f is this, basically. I would start with BFO, which is just the minimum. BFO, I don't know if there's a good name for it, because it's just a minimum of 3 different kind of unrelated dimensions. So like, yeah, you do this calc, or it's this, or it's this. I've just shown it visually here. Yeah, and then you chuck it in to this big fat formula. Oh, it's gone pixelated. But that's only if the web doesn't have longitudinal stiffeners. If it has longitudinal stiffeners, your alpha f is 1. So I think this is called the flange restraint factor. Like taking a step back, this is just to do with buckling, right? So if your flanges are restrained well, it's less likely to buckle, right? So let's again, I'm gonna draw that diagram. So that's your section, that's your beam, that's your supports. We have our load-bearing stiffeners, say the point load's acting here. We have a longitudinal stiffener, right? So take this part of the web right here, right? At the load-bearing stiffener. If we have a restraint in the middle, and we're talking about compression here, right? If it's restrained in the middle, it can't move left and right in the middle. Essentially, we've halved our buckling length. That's what alpha f is about. Yeah, so it's a reduction factor if your thing's fucking buckling out because of the the flange restraints and stuff like that. It's basically how well these are, how rigid they are, essentially. Yeah. So we're talking about shear, but we're also talking about compression. It just depends on what we're thinking about, like the perspective we're thinking about. Because anyway, I've said that a lot, but do you get what I mean? So you get what I mean? Oh yeah. The control is next to our general. Yeah, you can turn it off if you want. I don't need it anymore. Okay. Step 3. uniform shear capacity. So the reason why we needed VW and VB first to find VU. So remember, step 1 was the yield capacity, which is VW. Step 2 was the buckling capacity, which depended on VW, right? It had it in the formula, right? Now, third step, VU. So VU is equal to this one if, X, and this one if, else if, because one or the other. So it's dependent on your web panel slenderness, right? So basically, if your web panel it's the same thing as compression, basically, right? Because we're thinking about it like shear, force going down like that. If this is slender, it's going to buckle, right? That makes sense. So it's going to be governed by your buckling capacity. If it's compact, it's going to be governed by your yielding capacity, right? Because it's going to do a crush yield, right? That's all this means, right? So in terms of what slenderness ratio we're talking about, dP, right? Length to thickness. Makes sense? This is essentially it's a column, and we're comparing that ratio, right? Now there's some other numbers going on, and it's to do with material strength and stuff like that, but essentially it's the same thing as LE on R, right? Slenderness ratio. And so if we have a longitudinal stiffener in there, dP gets reduced, right? And hence your buckling, your effective length goes down, essentially. It's just less prone to buckling. Make sense? Cool. Okay. Lastly, shear capacity. So, if our section was uniformly distributed, such as this I-beam, we're all good. VV, which is our final step, is the same thing as the uniform capacity, right? Uniform shear stress capacity. However, if it's not, here's where we need to have done the solid mechanics calcs, because these directly plug into this formula. So if if we have this unequal flange I-beam, say that right there, that's the average, right? So when I drew that line vertically, what I mean is like, if I took the values of all these points and I averaged them over the depth, right? That's where, like, that might be the average there. Got it? So maybe it helps mathematically to think about it like this, right? Imagine this is like the height of someone, right? So it's like, oh, this is like a fucking ant or something. That's like another ant. Oh, this is like a really tall, like, fucking basketball player or something. It's like your average dude, average female, little kid, tiny baby, right? We get all their heights and we average it. It's gonna be somewhere there, right? Same thing. Yeah.
That was a good analogy.
Thank you.
Except the kid. And the ants.
Okay.
School for ants.
And so there's formulas for that, by the way. I'm glossing over the fact I didn't want to overwhelm you guys with all the solid mechanics yapping from earlier, but I've included formulas for it. There it is. So to find the max, the neutral axis is where the max is, basically. The max shear. So if this is a function of y, you plug in the neutral axis point. And whatever that is, that's where the max is. Get it? Average, you take the integral and you divide it by the depth. So in other words, now this is where the height thing kind of breaks down, the height analogy, because it's kind of a continuous thing. But when I'm talking about people, I'm talking about discrete things, right? But you basically take the average height of all these millions of data points, and you divide it by the number of data points. So that's what we'll do. So area of this whole thing divided by the depth of the beam, same thing. And that gives you your average.
Nice.
Okay. Yep. Any questions? That's shear capacity done. We haven't talked about load bearing stiffeners, but yeah.
What?
Dude, load bearing stiffeners is longer, but I'm not even sure if it's in the course for you guys. Like,
Suited flexural shear.
oh, sorry.
Shear design.
We haven't done shear and bending. Let's talk about shear and bending. So there's two methods. I would recommend using the interaction method. They did talk about the proportioning method as well, but I would say don't use it. Basically, I literally got so lazy. I just screenshot the lecture slides. It's basically, say the web. So we don't include the web at all for bending. We just take the flanges, and if that moment capacity of just the flanges can satisfy whatever external bending load, then shear and bending satisfies. That's what that method is.
Awesome.
But don't do it that way.
What?
Do it the interaction method way, I would say. So, basically, think about it like a number line, maybe. So here's 0. Here's phi ms, right? You guys remember what ms is? Section bending capacity. Phi is 0.9 reduction factor, right? Our external load, maybe we can think of this like a fuel tank or something, right? So this is max fuel, full. This is empty, right? If 75% or less, let's just say 70%. If our fuel, maybe it's not a good way to put it, like fuel. Let's think of it like a number line. Okay, forget what I said anything about fuel. Basically, if our capacity is creeping up, right, to 70%, let's say, or less, 75% or less. If our external moment is that, we have to use this formula, right? Oh, we can use that formula. That's actually good. It means that our external moments are nowhere near our capacity limit, right? But if it's greater than 75%, right? So if it's like 90% or something, right? We're getting pretty close to what the limit allows for, right? Like our external moments are getting pretty close to what's going to break the beam in bending. Then we have to use this formula. And it's based on that ratio of m star to ms, phi ms, rather. So it's like a reduction in whatever we got for step 4 of the previous thing. Make sense? That's VVM. And then we have to make sure that VVM, right? So VVM just means what we got in shear, and then we have to account for some moment. That's VVM, the shear and moment capacity combined. Okay, any questions? We haven't gotten to load bearing stiffeners. But you understand, like, each of these steps aren't that hard to do, right?
This week was a lot easier.
Yeah, that's what I'm saying. Like, flexion is the hardest week by far.
Have we already done flexion?
I haven't caught up with that too.
Have we done flexion already?
Yeah, 4 and 5 was.
Oh, that was easy.
Okay, sure.
Damn, everything's easy. We're fucking lucky.
Yeah, I'm just kidding.
Okay. Get a C?
All 3 different spectrums.
Yeah, okay. Load bearing stiffeners. So I've literally put a note here which says check whether this topic is accessible. It might be optional.
Awesome.
But with that said, let's talk about it anyway, just in case it is. Because in geotech, I had this topic which I said was optional, and then it ended up being in the finals. So I'm not letting that happen again. So you have 1 point load, right? Let's say, and then we have 2 reactions. We said before how much of that says in the middle. How much is each reaction taking?
Half the.
Exactly. Right.
Exactly.
And then yeah, it will change based on how many point loads you have, right? So you have 2. Now these are matching P. So you have 3. Now the reaction is more than P, right? Okay. Now it gets a bit cooked. Sorry, I know this is really difficult because it's fucking all pixelated and shit. Should I rejoin it? I'll just let it sit. I'm pretty sure the quality will get a little better. Do you see what's happening here? Okay, basically think about it like this, right? We're talking about bearing. We're gonna be using the word bearing now. Okay, so bearing. Geotech. You guys have all done geotech, right? Do you know how we talk about
Isn't that boring?
No, bearing. So, fucking good one. Shallow footing design, right? For example, do you remember how we talked about Q, bearing pressure, Hansen's equation? Are these things making sense? Hansen's equation is basically we have our foundation, right?
All the components you have to add.
Yeah, that one, yeah, the really long equation, right? We have a force going through this column and into the pad footing and then into the ground. What does the ground do? The ground has a natural response back. It reacts, right? It squashes and it wants to push back against that footing. That's bearing, right? So bearing is this force over an area, essentially, right? So the bearing area is the surface area of the pad footing that's pressing against the ground, right? So basically the idea of bearing is that it's saying that like all point loads can be considered as things that are spread out over a certain bearing area or bearing width. But if that bearing width or bearing area is particularly small, it's going to be a bit worse. Like it's going to take on more force per unit area or whatever, right? Does that make sense? Anyway, I'm kind of digressing. This, what I've drawn here in red, the distributed load, that's our point load that we talked about, but we've considered it as a uniformly distributed load now. And that width is our bearing width. That width that it goes over is a bearing width, because every point load is technically not infinitesimally small. It has some kind of width that is applied over, right? So, like a knife, right? When you're chopping like a fucking cucumber or something, right? It has a really small bearing width that you're chopping it, and so that force is like an extreme point load, so it can kind of it can slice through, right, basically. But if you do the same thing with a mallet on a cucumber, just fucking squashes it, and then you have other things going on, right? Anyway, my point is, think of point loads. When you zoom in enough on a point load, it's gonna have a certain bearing width in real life, right? That's what, Anyway, I'm gonna shut up for a sec and just concentrate on what's in front. So it's really annoying because I would like to show you guys this while zoomed out, but I have to zoom in. So BS, right, is the applied loads bearing width, right? Let's talk about just universal beams for a second, right? Through the flange, at a gradient of 1 to 2.5, that force is going to spread out and increase in like the area that it affects, essentially, right? And then through the web, that gradient changes to 1 to 1. right? So now we have all these different terms. BBF is what the bearing width would be at the bottom of the flange, right here. And then BBW doesn't get any better than these terms. Is is increased from the flange to the middle of the web. Now we said about shear that the max shear happens in the middle of the web, right? So that's kind of what we care about in the end. It's BB, the bearing width that's been transferred and increased until the middle of the web. That's everything, right? D2 is slightly different to D1. So you remember how in the previous part we talked about D1 as the clear depth between the flanges? D2 has a fucking weird definition, but it's essentially the same thing. Kind of. It might be a bit different based on the shape, but D2, twice the clear distance from the neutral axis to the compression flange.
Ooh.
So this would be weird if you had like a T-beam, for example, where compression flange. Yeah, anyway, you get what I'm saying, right? There's some edge cases where it's different to D1, but
what if there's compression on both sides of the flange on either flange?
then it's
You know what I mean?
so like that. Then it's axial compression.
No. I mean, imagine a beam that has two cantilevers on the end. Then the compression edge is on both sides.
You're talking about a beam that's split in the middle and is being pushed.
No.
Like the supports are not at the ends.
Yeah, the supports are in the middle somewhere.
Oh,
That
like that.
extends further out.
Yeah, so now you got a little bit of compression on the top and a little bit of compression
But-
at the bottom.
Yeah, I know what you
So
mean.
now
But
you don't have a compression edge because both of them are compression flanges.
but we only care about where the point load is applied.
Oh, at the
At the point
specifically
load.
at the point load.
Yes.
Okay.
So and then in that case, right, it might look like this, right? And then in that case, your stress distribution will look like whatever, right?
Okay.
So there'll always be either one compression flange, and if both flanges in compression, you have axial compression,
Yeah.
which is that one.
Do we need to know why that force spreads out more in the flange and then
Not really.
that ratio?
Nah.
Just
If you care, it's probably in the appendix. Sorry, not the appendix. It's in the commentary for AS 4100, I bet.
Not even the appendix, just the commentary.
There's
Give
literally a
us a
separate
second, hold-
document called the supplementary commentary. It's for people who ask like
Silly.
there's like questions that
Smart ass question.
but yeah. So
Sue.
interior force, it's kind of symmetrical on both sides, right? End force though.
Tony has a diary room.
In end force is where the beam ends, right? And so you have a point load that is applied near there.
Yeah.
Obviously, it cuts off, right? So BO is where you have an edge which cuts off, essentially, right? So we care about BB at the bottom here. You just have to consider the geometry of the beam, basically. So if it ends short, like you have your point load applied near the edge, then your bearing width in the middle of the web is going to be probably shorter than if this point load was applied in the middle of the beam, right? So what I mean is like, if the point load is applied in the middle of the beam, you follow the interior force steps. But if it's applied like here or something like that, you probably gotta consider an end force situation. Make sense?
Mm-hmm.
Okay. Now there's formulas, but it's easier if I just explain the concepts and you just go back and slowly look through the formulas. Okay. There's a similar thing that happens for bearing that happens for shear, right? Because they're very, very much the same. So bearing is bearing capacity rather. Oh fuck. Now the internet's just going so shit that like it's not even catching up. Man. Oh, there we go. This is kind of readable now, right? We also have yielding capacity and buckling capacity, right? So that's denoted by RBY and RBB, right? So similar to VW and VB, right? We had to find BBF, right? Which was, I might just help if I draw it. You have your point applied here. Remember this one here. I might not do an orange because I think when it's lagging, it doesn't like orange very much. This is BS, right? The width for the applied UDL.
Yeah.
Spreads through the flange.
Yeah.
And then at the bottom of the flange there, whatever that distance is, I just said I wouldn't use orange, but I used it. That's BBF, right? And that's what that formula is, right?
Yeah.
Cool. Now BS is sometimes given in the question, but sometimes you have to calculate it geometrically, and that's when you have to look at it. Basically, you just have to look at this this diagram and figure it out based on your shape. Okay. Now shear buckling in bearing, right, is essentially the same thing as the buckling in compression formula for a column, right? This should look super familiar, right? Does that look familiar to you guys? It literally has alpha C and everything. This is what your assignment was
Holy bro.
on. Basically, think of it like this, right? For a column, let's just talk about a column for a second, right? This is your area, right? And then it can buckle and all that. We have effective length. We had to calculate the radius of gyration, things like that, right? Similar idea for your bearing, the web buckling in bearing, right? But it looks like this instead. That's BB, is the amount of web in shear. And that is TW, that dimension. And D1 is the effective length. Does that make sense?
Interesting.
Yeah, and so BB is important because you know how we had to find all those things that like increase the bearing width and spread it because it goes through the flange, goes through to the middle of the web. BB is what that width has become at the middle of the web. Yeah, and then we just do a fucking literally we just treat that like a column and do a buckling check. And just based on that shape that I drew here, where do you think the minor axis is? So would it bend this way? So direction 1 that I just drew, or direction 2?
The directions were lagged.
Oh, direction 2. I'm gonna redraw and bigger.
Side to side.
Direction 2, right?
Yeah.
Yeah. That's the way it's going to buckle. There's no way it buckles the other way, basically. So we don't have to do a single check. We don't have to do like RX, RY, that kind of shit. Yeah. Anyway, there's some steps to follow. We assume KF, so KF is a form factor. We just take that as 1. Like, no need to check that shit.
Yeah.
Alpha B, because we know, I think it's 0.5 because it might be one of those, oh fuck, it's lagged, isn't it? We take alpha B as 0.5. It's one of those rules where it's like it's been hot rolled, all that shit. Anyway, we're just doing it for the fucking web, right? It's always 0.5.
Cool.
Okay, now flange restraints, right? So how do I say this? Usually 2 flanges are restrained because we're dealing with I-beams, right? These are welded, like they're not welded together, they're hot rolled, but they're rigid, right? And we have 2 of them. If we have a T-shaped I-beam, so like one of the flanges has been cut off or something, then we only have restraint at one flange, right? And then all of a sudden, your buckling action, right? It's essentially only restrained from one side, so it can kind of like cantilever, buckle out like that, right? So it's worse. Got it? Yeah. And then we do all that shit with modified slenderness ratio, and then we do all that to find alpha C essentially, and just use the weak 2 notes basically. Okay. Did we need stiffeners? We just checked everything as if we didn't have stiffeners. If it fails, now we add stiffeners. Now we add load-bearing stiffeners, right? Same thing, add on more, right? Those red things, right, in the drawing before. Load-bearing stiffeners. AS is the area of stiffener in contact with the flange. That's this area here. Coloring it in, right? So you had to take the capacity that we found in part A, add on this new capacity. The yield strength of the stiffener, it might be slightly different to that of the web or of the flange or whatever. We won't really be talking about the flange for bearing, but yield strength of the stiffener might be different because yield strength is based on the thickness of your metal plate, right? So it might vary slightly. Shear buckling capacity in bearing with load-bearing stiffeners, right? RSB. So, same thing, compressive buckling, right? Formula. Things are slightly different now, okay? Because, so before, okay, ignore this red thing, right? My stomach's fucking churning, sorry. So before, we considered this, right? This shape. Here, we had to find TW multiplied by BB, right? And then your effective length was D1, right? Now, oh, and we said that it bent this way, right? Side to side. What we do with load-bearing stiffeners is we add on additional bits like this. So we almost have like a plus shaped column. Like a column which section is plus shaped, right? Which way is it gonna buckle now? Either, but we simplify it because we're Siebes, basically. We just assume it's this way. Yeah, and actually you'll see in the formula it's kind of dumb. You kind of disregard this whole middle part. Yeah. So you take the I and AS values of just the stiffener, so you don't include the web anymore, right? Yeah, there's just slightly different rules. Instead of them giving you LE on R, you have to calculate R separately, but they give you LE. Okay. You chuck it into your modified slenderness ratio, and then you chuck it into alpha C. There's a bit where you need AG. Yeah. Oh, sorry. This part of the equation, right? So for basically for the buckling, we only consider the stiffeners now instead of considering the part of the web, right? That's in bearing. But when you're calculating AG, you need to add them together. You need to add in the green area, and the green area. Sorry. The green area is the part of the web which is in bearing, and the red area is your stiffeners. So you got to add those two together to get a plus shape, and that's AG, the gross area. And then that's pretty much it. And then you check whether R star, so R star is your reaction force, which is greater if you have like 3-point loads, for example, or P star, which is greater if you have 1-point load, for example. Yeah, check if those are less than your bearing capacity with the stiffeners, and if they are, you're good. Did I write that right? Ah, I should update these notes. There's some mistakes. SB, SY. And one last check, and this is the end of the yap, I swear. BES is the width of the edge of the stiffener. That just has to be less than a certain number. And that's it. Any questions? Fantastic. I'm going to end the recording. I hope I've been recording. Okay, good.